In the previous video, we established a result known as Bézout's lemma, and in this video, we'll explore some of its consequences. So here was the theorem. Multiples of the GCD of A and B and linear combinations of A and B are the same set. But why does that matter to us? Well, as a corollary, the greatest common divisor is the smallest positive linear combination of AB over the integers. The proof is pretty direct, okay? Linear combinations of A and B are exactly the multiples of the GCD. So instead of looking for the smallest positive linear combination of A and B, we can just ask what's the smallest positive multiple of the GCD, and it's definitely the GCD times 1. And since the two sets are the same set, their smallest positive elements are the same. So the smallest positive multiple of the GCD must be the smallest positive linear combination of A and B. So the GCD of A and B is the smallest positive number you can ever get by doing a linear combination of A and B, which is kind of interesting. Here's another corollary. If there exist x and y so that ax plus by equals 1, then A and B must have been relatively prime. And the proof is again quite fast. If 1 is a linear combination of A and B, well, since the set of linear combinations of A and B is the same as the set of multiples of the GCD, then 1, which is a linear combination, must be a multiple of the GCD. But the only factors of 1 are plus or minus 1, so the GCD must be plus or minus 1, and it's definitely not negative, so the GCD must be 1. Here is another very important result that we're going to use many, many times. Suppose A is a factor of the product B times C, and assume that A is relatively prime to B. Then A must be a factor of C. Well, the proof doesn't take that long, but it takes a little bit. So since A and B are relatively prime, their GCD is 1, so I can express 1, the GCD, as a linear combination. So there exist ax and y so that ax plus by equals 1. If I multiply this equality by c, I get acx plus bcy equals c. And therefore, note that a is definitely a factor of acx, because there it is, it's a times cx. A is definitely a factor of b times c, so a is a factor of b times cy. Why is a factor of b times c? That was our first assumption here. So if a is a factor of b times c is definitely a factor of bcy, and factoring is transitive as we've already established, so a must be a factor of bcy. Therefore, a must be a factor of acx plus bcy. It's a factor of this plus a factor of that, therefore it's a factor of the sum of those two things. If a can be factored out of each of these things, then it can be factored out overall. But acx plus bcy is exactly c. Therefore, a is a factor of c, and that was the desired conclusion. So if a is a factor of a product and it's relatively prime to one term, then it must be a factor of the other. This is something we're going to use, I'd conservatively estimate 20 times as a step in a proof somewhere else in the course. So again, if one integer is a factor of a product and that factor is relatively prime to one of those two integers, then it must be a factor of the other. But we do need to be pretty careful when applying this result. We had the given that a was a factor of b times c and the conclusion that a was a factor of c, and we definitely used the assumption that a and b were relatively prime. A lot of students try to make the following claim. If a is a factor of b times c, either a was a factor of b or a was a factor of c. But this is not a true claim in general. Just because a is a factor of b times c does not mean you can immediately conclude a is a factor of b or a is a factor of c. For example, let's let a be 6, b is 2, and c is 3. Well, b times c is 6, and definitely 6 is a factor of 6. So a is a factor of b times c. But both a is a factor of b and a is a factor of c are false statements. 6 is not a factor of 2, and 6 is not a factor of 3. So if you want to proceed from knowing one number is a factor of a product and be able to conclude that it must be a factor of one of the terms in the product, generally what you need to also have at your disposal is that the factor was relatively prime to one of the terms. Then you can conclude it's a factor of the other one, but without that bit of knowledge, there's no immediate way to get to the conclusion unless there was other information at play, perhaps. Here's another consequence of Bézout's lemma. If D is a factor of A and D is a factor of B, D is a factor of the greatest common divisor. In other words, any common factor of A and B is a factor of the greatest common factor. We've basically proved this already. D is a factor of A and D is a factor of B, so it must be a factor of any linear combination of A and B. But the greatest common divisor is a linear combination of A and B, and therefore D is a factor of it. Here is yet another application of Bézout's identity. Suppose A is relatively prime to B1 and also relatively prime to B2. Then A must be relatively prime to the product B1, B2. This is a theorem a lot of students kind of say, yes, isn't this obvious? Because when you think about the prime factorizations, and immediately you've got to stop. We haven't introduced what a prime number is, let alone prime factorizations. And the fact of the matter is, factoring numbers is very difficult, a very important result that we'll see later. Euclidean algorithm is a way to find greatest common factors that doesn't actually rely on anything about prime numbers or prime factorizations, so it's very useful to us. Okay, so this result here we're going to prove using Bézout's identity, which has nothing to do with primes. It only, in this statement, has to do with two numbers being relatively prime. So let's denote this number here, this GCD, as C. The goal is therefore to show that C is equal to 1. That would conclude the proof. However, whatever it is the greatest common factor of these two numbers, so it is a factor of both numbers. Now let's suppose that D is some positive integer that's a factor of both C and B1. So D is a common factor of C and B1, and it's positive. That's what we've assumed. Well, D is a factor of C, but C was a factor of A, and factoring is transitive, so D must be a factor of A. Okay. But now that we have D being a factor of A, and we already had D as a factor of B1, if D is a common factor of these two things, we established on the previous slide that it must be a factor of the GCD. But these two were given to be relatively prime. So D is a factor of 1, and D is positive. There's only a single positive factor of 1, and that's 1 itself. So the only common factor of C and B1, the only positive integer, which is a factor of both, must have been 1. If the only positive common factor is 1, then certainly the greatest common factor is 1. So C and B1 must be relatively prime. Remember, C is this greatest common factor, and we're trying to show that that's 1. Our goal is to show C is 1, and we've just shown it's relatively prime to B1. So if C is relatively prime to B1, and we did already know that C must be a factor of this product, but it's relatively prime to the first term, so it must be a factor of the second. So whatever C is, it's actually a factor of B2. But again, C is a factor of A. We already had this way up here. And we've just concluded that C is a factor of B2. Well, if something is a factor of two numbers, it must be a factor of their GCD. But again, we were given that A and B2 were relatively prime. C is a positive number, which is a factor of 1, so C must be equal to 1, and that's exactly what we were trying to prove. So if A is relatively prime to two numbers, then it is relatively prime to the product, and we were able to prove that without relying on any notions of prime factorization, a notion that we haven't even introduced yet. Here is yet another consequence of Bézout's lemma. Suppose that A is equal to D times M and B is equal to D times N, where D is the greatest common factor of A and B. Then those other factors, M and N, must be relatively prime to one another. Another way to put this is, if A and B have greatest common factor D and you cancel that out of both of them, what remains of the two numbers are relatively prime to one another. Well, let's suppose that we have an integer which is positive and is a common factor of M and N. Well, if X is a factor of M, then X times I equals M for some choice of I. And if X is a factor of N, then X times J is equal to N for some choice of J. Multiply both of these by D. So what you end up with is dxi equals dm, but dm is a. But you also get dxj is dn, and dn is b. So what you conclude is that dx is a factor of a, and dx is a factor of b. So dx is a common factor of a and b. Since x is at least as large as 1, we conclude that dx is at least as large as d. So dx is some common factor of a and b, but d was the greatest common factor of a and b. So here we have the biggest of all common factors, and here we have one particular common factor. It's not possible for this to actually be bigger, so it must be less than or equal. But if dx is both bigger than or equal to and less than or equal to d, they must be equal. And if dx is equal to d, then x must equal 1. So if any positive number is a common factor of m and n, x had to equal 1. So the only positive common factor of m and n is 1, and that concludes the proof that in fact they are relatively prime. So let's talk about what we've gone over. There's a lot of statements that we've introduced that students think are obvious. If a number is a factor of a product and doesn't have a common factor with one term, it must be a factor of the other. Or if we cancel the greatest common factor out of two numbers, what remains of the two things we started with are relatively prime to each other. There's nothing else to cancel out. If a number is a factor of two numbers, then it's a factor of the GCD of those two numbers. But more importantly than stating them as true, we were able to construct formal proofs. Okay, so these are now unambiguously true statements, and we proved them. Okay, so Bézout's identity is a very important result, so do remember it. Linear combinations of two integers form exactly the multiples of the GCD, provided they were not both 0, because in that case the GCD would not even exist. So specifically, the GCD itself can be expressed as a linear combination of a and b. This is a step that's going to show up a few times as a single step in a proof later on. The GCD of two numbers can be expressed as a linear combination of those two numbers.